And to do that, we're going to make an array out of our data set .values. So this is each individual point is an array. I'm going to split our x and our y. So our x here is going to be the first 4 rows, or 4 columns, sorry, while our y here is going to be just the last one. So our y is the class or the species, whereas the x is going to be the sepal and petal width and height. So our validation size is going to be important as well. 20% of our data, so just 0.2. And then so seed, we're just going to set the seed to a number because you could split out this data a couple of different ways using like a random seed or randomly pick the validation data set. We're going to just keep it constant throughout. So this is going to be the actual step that creates the validation step. So we're going to have an X train and X validation. We're also going to have a Y train and a Y validation. So those are our data sets, X and Y, for the train validation. And we can actually use this very convenient model selection module that we imported earlier. And it has what's called the train test split. So it's actually going to break this data set apart for us. And test size we specified earlier as validation size, and then random. Let me check this really quick. So our random state is going to equal the seed that we set before. So let's make sure this runs, and yes, it does. It was very quick. So as soon again as that asterisk goes over to a number, we know it's completed. All right, and now we're going to make some more specification, test options, and evaluation metric. For this, we are just going to do scoring equals accuracy. So this, spelled that wrong, is just going to be the percentage of correct predictions versus wrong predictions. So how often does the Y that we predict with our algorithm actually match the class or species of the flower that we were hoping to find? So let's Shift Enter, run this cell again, and let's move on to actually building our models. So again, we mentioned the 3 models that we're going to build are a logistic regression model, which is the linear regression model, and then the k-nearest neighbors model, and a support vector machine model. So the last 2, the k-nearest neighbor and the support vector machine, are going to use some kernel methods, so they're going to be nonlinear metrics, whereas the logistic regression is going to be a linear model strictly. So let's do that now. We're going to make an empty list of our models, and then we can append to it each model that we want. So logistic regression, this is going to be our first one. And that's just denoted as such. And then we can move on. So we are going to get to the KNN, which is the k nearest neighbors model. And that is denoted as such. And then our last one, which is just going to be the support vector machine. And that's actually denoted as support vector classifier, which is good. We're doing a multi-class classification problem, so that is exactly what we want. And here we are going to evaluate each model in turn. Actually, before we do this, what I want to do is actually just load these. So we have our models, and I want to actually print out the models so we can maybe learn a little bit more about them. So this is a little jumbled, but you can actually see the different models in here. So here's our logistic regression, and here's our k nearest neighbors. So if you look at this, it's actually using a k equals 5 nearest neighbors right here. We talked about setting the k value before. And we're not going to mess around with changing that value for now. We're going to just leave it at that. And here's our support vector machine. And so it is using the RBF kernel. This is a pretty common kernel. So we are going to move past linearity here and do that. So we have one linear and two nonlinear methods. All right, so now let's move on to evaluate each model. So we're going to make a results list, and we're going to have a names as well. We want to keep track of names. And then we can do for name model in models and k-fold. This is going to be our actual cross-validation here. And we're going to do number of splits equals 10, random state equals seed. So this is going to split the testing or the training data into 10 different parts and just do a train test split as it's evaluating these. So let's get some results equals model selection dot cross val score. So this is actually doing like a mini cross validation step in the training. It's using the data only in the X train and the Y train. However, it's splitting it into 10 parts and using 9 of them to fit the data, and then it's testing it again against that last part. So our scoring is going to be the accuracy, which we set earlier. CV results names dot append name, so we have the name of the model, and then we're going to output a message here so that we can understand which one is performing the best. So you can substitute variables into strings in Python using these percentage. You can also use a dot format. Either one works fine. It's certainly up to you. Mean, and then CV results standard deviation. So we're going to output the average or the mean accuracy for each of these models in this train test split, and as well as the standard deviation. So it's Python, so we have to include a print message in there. All right, so let's see how these guys do. Again, we are splitting our data, just the training data, into 10 parts, and we're gonna fit some of it and then test or score that last little part. And that'll output an accuracy, the mean accuracy for those 10 splits, as well as the standard deviation. So let's try to shift enter, and wow, here we go. So our logistic regression model, an accuracy on the training data of 96%, the k-nearest neighbors 98%, but actually the support vector machine wins out with a 99% accuracy, and actually the lowest standard deviation as well. So not only is it the best, but it is consistently the best for this classification problem. However, I should be careful in saying that, because remember, this is still just the training phase. So it's the most accurate in the training data, but that's not what we care about in machine learning. We care about making predictions. So let's move on and actually try to make some of those predictions, do that cross-validation step with the validation data that we set apart earlier, and ensure that we're not overfitting or even underfitting our training data. So this is where we want to check that it can generalize, and to do that, we are going to make some predictions on validation data set. Okay, so for name model, in models, we want to do a model.fit, and this is just going to refit on the training data. Should give us exactly what we had before. But then we're also going to have this prediction step, which is going to be model, and we are going to be predict X validation. So this is the x data, the length and width that it hasn't seen yet, and we're going to make predictions on that. And we can output the name, accuracy score, which is going to be comparing our Y validation to the predictions. Let's make sure we spell things right here. So this is comparing the actual answers, the Y validation, to what our machine learning algorithm thinks it is. And we're actually going to print a classification report, which will give us some more information on the predictions that we've made. All right, so let's see this. Everything looks good. We should be good to go. Shift Enter, and here we go. So logistic regression down to 80% on the validation data. The k-nearest neighbors, 90% accuracy. The support vector machine is still the most accurate, coming in at 0.933. And this has some information about like the precision for each class. So if we look at these, we notice that this third class is the most difficult. Well, not for the k-nearest neighbors, but it is difficult for each one. So actually the SVM classified this iris setosa and this iris versicolor with 100% precision in each case of the validation data. So we've done our validation step, and we can now say confidently that this support vector machine with its RBF kernel is the best model for this classification problem. And we can say that confidently because we know we're not just overfitting the data here in our evaluation on the training, but we did a cross-validation step to make sure that we can generalize to new data, and we can generalize with 93% accuracy, and that is better than the other models that we explored. So this brings us to the end of this project. We've compared and contrasted these three models. We took a look at doing some necessary steps in machine learning. We learned how to import different packages and some common libraries used for machine learning in Python, being the scikit-learn package is probably the most common. We loaded a data set into Python. This is going to be essential for almost all of these applications. And we explored some of the data features. We did some data visualizations. A very important step is understanding the data so that we can make accurate biases going into our training step. We want to make as many assumptions about the data as we can going in, because remember, the data by itself is not sufficient. We learned how to split out a validation data set using this train test split function, which is very convenient to create an X and a Y train and validation data set. And 20%, this is pretty common for a validation size. You typically want to use about 80% for training and 20% to make sure that your algorithm can generalize. We explored the scoring metric of accuracy, and then how to actually generate models and the specifics that those models come with. And this is using the scikit-learn packages as well. We learned how to evaluate those models on the training data and how to actually fit the models, doing a actual scoring on the training data. And then we made sure that our models could generalize by making predictions using the model.predict function on the X validation data and compare that to the Y validation to get an accuracy score back out. And we also use the classification report so we can learn a little bit more about how our algorithms are performing. So this is the hello world of machine learning. This is as basic as it gets. However, you can now confidently say that you have used a supervised learning algorithm to solve a classification problem in Python. So congratulations. The sky is the limit from here. And we are going to continue getting slightly more complex and diving into this a little bit deeper. But hopefully this tutorial helped reinforce some of those concepts that we talked about in the videos. It's always more fun to get your hands dirty and actually do some of the programming yourself. So thank you very much for listening. In Unit 3, we're going to cover unsupervised models. So those are going to be trained and tested in completely different manners, but you have the foundation now and you have some Python programming skills. So that should be fun and enjoyable and beneficial for everybody. Thank you very much for listening.